Right, so yeah, thank you very much for inviting me to talk to friends of Imperial. Rod has introduced me, but just to confirm, I'm a professor of structural engineering, and that's what I spend my time doing, teaching and research in, with a focus on steel structures. I'm involved in codes of practice quite a lot, particularly European, but also in the US and working with industry. And I've got an active research group who are doing the hard work behind the scenes. And here's some sort of contact details and further information if you want to get in touch. We do different things in the Steel Structures Research Group, but metal 3D printing has probably become the most important one for me. Sort of most of my resources are devoted in this area. But we also do quite a few other things, as you can see on the screen here. And so this is what I'm going to talk about today. So the bridge in question is called the MX3D bridge. It's in Amsterdam. And I'm going to talk about our role in the project, and in particular some testing of material components and the full bridge and simulating it. And also, you know, what do I think the future looks like to some extent in this area. So this is what the bridge looks like. It was printed by the company MX3D. So they're based in Amsterdam themselves. The structural engineers, Arup, were employed as the designer. And then at Imperial, we did the testing and analysis of the bridge. So we tested the full bridge, but also parts of the bridge to destruction. And we did this at various stages, both during the construction process and then after construction was finished. And it's now open to the public. So it's a footbridge. It's 10.5 meters span and 2.5 meters wide. There's about 4.6 tons of printed material. It's stainless steel. And then there's an additional 3 tons for the deck, finishes and end beam. And these are essentially non-structural elements. The printing took about 12 weeks in sort of total print time, and this was spread over a 6-month period. Printing wasn't sort of done at full speed because there was a bit of learning and checking as the process was going on. And it's a tubular structure, so all of the components are hollow, and then there's 2 main thicknesses, 3.5 millimeters and 8 millimeters. And the process that's been used to print the bridge has got a nice acronym called WAAM. So it stands for Wire Arc Additive Manufacturing. And it's basically an adapted welding process. So it's like a welding torch being controlled by a robotic arm and then following the shape prescribed by a digital model. So in fact, the technology to some extent is quite familiar already to the industry. We've been welding things for a long time. And the hardware, 6-axis robotic arms, are not particularly expensive, and they're used in a wide range of industries. And then the actual material used for the printing is wire. And again, this is just standard weld wire. I've got here a short video which is showing an element being printed. And you can see the robot moving layer by layer, printing the structure up vertically. And the bridge was built in 4 pieces, which were 2.5 meter length each. And then they were manually welded together to make the full span. So material testing. So the first thing we wanted to know was what are the sort of underlying mechanical characteristics of this material. And you normally obtain these by doing what are called coupon tests. You can see one on the screen. So we put the material in tension, we get the load and extension, and we convert that into a stress strain curve. And this characterizes the material response. Now, this is a layered material, and so we thought there's likely to be an influence of direction of testing. So we cut out coupons at different angles to the print layer direction. And we also thought that the surface finish would have an influence on the behavior. So we also milled down some of the coupons to get them flat. And then we conducted separate tests, some on machined material to really get the underlying material characteristics. And then some where the surface roughness was left in place to get the as-built characteristics. And the bridge was not machined in any way after it was printed. So the actual bridge was left in the as-built state. So here are some typical stress strain curves. So you can see the results for the coupons in the 0, 45 and 90 degree directions. And generally the mechanical properties were good, some degree of anisotropy, so different characteristics in different directions, but overall good strength, stiffness and ductility. What I've got here is a series of numbers in this table, which are the ratio of the as-built mechanical properties to the machined mechanical properties in order to reveal the detrimental effect of the surface roughness. And you can see for most of the properties, so the Young's modulus and the yield strength, for example, you have around about a 10% reduction in strength and stiffness as a result of the surface undulations. But over here, this ultimate strain, this is a measure of the ductility of the material, you have a more severe reduction in the 90 degree direction. And 90 degrees is where you're pulling across the layers. And so this material is affected quite strongly by the direction of loading. And what's going on, you can see on these photos. So here's a coupon where we're pulling along the line of the weld layers. The top one is before testing. The second one is after it's fractured in the middle. And you can see there's a good amount of elongation here before failure. So that's a ductile response. 45 degrees, it's a bit less ductile. And then 90 degrees, it's quite a lot less ductile. And the reason for that is in the 90 degree direction, you've got your cross-sectional area kind of going up and down, and all of the deformation tends to run into the minimum cross-section. And so the strains become very much more localized, and therefore you get less ductility over the full length of the coupon. So that's logical. And you can actually see it on these strain plots. So we used a method of measurement called DIC. So it's not Diploma of Imperial College, this one. It's digital image correlation. And it's a sort of non-contact measurement method, which enables you to get much more information than traditional measurement techniques. But what these are showing you, the first set of diagrams here are for the machined coupons at different angles. We've got a couple of intermediate angles that we looked at as well. And the red region is the region of high strain. And these red regions are quite large. And that means that the high strained zones are quite widespread, and that leads to a nice ductile response. And that happened in all directions, really, for the machined material. But when you look at the as-built material, it's still true that you've got widespread zones for the lower angles. But when you get up to 90 degrees, you can see it's very much more concentrated. All of the deformations running into that minimum cross-section, and that has a negative effect on ductility. And what we also found is that, as you'd expect, print quality is important, and the technology is still evolving, and print quality is getting better. And of course, the better you can print it, the lower the surface roughness, the less this sort of localization issue becomes important. Okay, so let's look at the material. So looking at some components now. So we printed components of similar dimensions to some of the key parts of the bridge. And we printed regular cross sections so that we could compare their behavior to normally produced sections, and we could predict their behavior using current design codes. A feature of this technology is that you get more geometric variability than you get with conventionally produced sections. And you can see some of the surface roughness, for example, on this tube. But we really wanted to capture the geometry as accurately as we could. You can't just use a vernier because the thickness and so on is different at all different points. So we used 3D laser scanning, and all of the sections were tubular. So the problem with a tube is you can scan the outside, but it's not so easy to scan the inside. So we had the idea of trying some silicon casting of the inside, a bit messy, but we created a silicon cast, which we got a bit better at pouring it later on. And then we pulled out the silicon cast, having sort of lubricated it and so on, and scanned the cast, and then joined the inside and outside to get a full sort of 3D representation of the sample. And at the ends of the tubes, we could actually scan both the inside and outside. It was sort of nearer the middle that we couldn't see with the laser scanner. So we could actually confirm the accuracy of this idea of joining the two bits together. And what that allows you to do is get really detailed statistical information about variation in diameter, variation in thickness. And this is important for later on when we're looking at safety, reliability, and so on. So we tested a series of different geometries, different sizes, different proportions. And we typically got, so these first ones are short compression elements, and you can see the failure modes here, which is, it's called local buckling. And what we also did is we made some comparisons with current design codes. So on this graph, I've got how much load the cross-section could carry divided by the area, cross-sectional area of the section multiplied by its yield stress. And then on the horizontal axis, we have the slenderness of the cross-section. And that is talking about how wide the cross-section is relative to its thickness. And what we found is when we plotted our test results, if we plot our test results based on the machined material properties, the results are down here, and they lie below the sort of current design curves. So that would be on the unsafe side in terms of a prediction. Whilst if we used the mechanical properties from the as-built coupons, what we refer to as effective mechanical properties, because they have the influence of the surface undulations, we're normalizing by a lower strength, so the points move upwards. And actually, they're now quite well predicted and on the safe side by existing design codes. So that was quite encouraging that these things are behaving, roughly as we're used to. And provided that we take into account the detrimental effect of the surface roughness, we get reasonable predictions from existing standards. And we did the same thing at member level. So in this photo on the right, this is a long column. It's about a 2-meter long column, a circular cross-section, and we loaded it between what are called knife edges, which allow the ends to rotate freely. So we put it in compression and it buckled. And again, using the digital image correlation system, you can get detailed information about how it's buckling. And you can see this sort of localized effect as well as an overall buckle. And if we plot the data on, so we're now talking about member buckling. So this is called a relative slenderness here, which is about the length of the column. Longer columns are moving to the right, and same as before on the vertical axis. Actually, the data points, these ones are plotted based on the as-built material again. and they're following pretty closely the existing buckling curves. So again, this gives confidence in the fact that whilst this is a new method of production, things are still behaving roughly as they should do. Okay, moving on to the bridge. So we wanted to test the bridge during construction at various stages to make sure things were on track. And then the final bridge we wanted to test, and this was part of the safety verification and approval process. So the local authority said, we need to demonstrate that this bridge can take as much load as an equivalent bridge, normal bridge, would be designed for. So this process started at the end of 2017, and the first 2.5 meters was printed at that stage. And we had relatively crude loading equipment that we took over to Amsterdam and carried out some tests, took some measurements, and it was performing well and performing roughly as we'd anticipated from a finite element model that we'd created. We went a second time in July 2018 when the full length of the bridge had been printed, and you can actually see the substructure here, which is you know, an interesting sort of organic shape. We went a third time when the deck plate had been put in place. And we carried out tests, what we called the serviceability tests, which enabled the bridge to be open in a temporary way, in a controlled way to the public. And then the final set of tests was in September 2019, when we applied the full design loading that the bridge would be subjected to normally, and in fact about 20% beyond that level. So some of the photos and so on. So two basic loading scenarios we considered. First one was we were pushing outwards and pulling inwards on the handrails. And this was representing crowds of people on the bridge, sort of having fun and pulling the bridge in and out. And you can see some jacks here that we used to push the bridge out, and then we sort of reversed them to pull the bridge inwards. And then the other main load case was vertical loading. And in this case, we used water tanks. So the water tanks are 1 meter cube. So you fill them up with water, and that's about 1 ton of loading per water tank. And you can see us filling up the tanks. We were trying to keep this relatively uniform. So we got uniform loading along the length of the bridge. I should say this was in Amsterdam, but we put an England flag on the bridge. And that was because the World Cup was going on at the time. We were showing our support. And the bridge deflected about 14 millimeters under the 4 tons of loading. And again, this was similar to what our FE model was predicting. So that gave us confidence again to sort of continue. Third set of tests, you can now see the deck is in place. So the deck is a stainless steel plate, but this component wasn't 3D printed. This was just welded in place to the 3D printed bridge. The loading here comes from a combination of concrete blocks and also water tanks. And the general idea with our testing is we didn't want to be physically on the bridge whilst we were putting high loads on it. And so water tanks were quite a good way of having relatively controlled means of loading without needing to be on it. The bridge was a bit stiffer with the deck in place, which is what you would expect. And it deflected about 25 millimeters under the 10 tons of loading that we applied in this set of tests. And that set of tests enabled the bridge to be open to the public for the first time in a sort of controlled way. And the controlled way was in what's called Dutch Design Week, which is like an exhibition of innovation in the Netherlands. People were interested in it. People were walking on it. This one group here were trying to test it to destruction. I think they started jumping up and down on it. And at one point, there was actually a bit of a cracking sound, which was a bit concerning, or very concerning. But in fact, it was one of this group had dropped their bag onto the metal deck. So it sounded a little bit bad, but in fact, was no problem.
At least they weren't going to fall in the water.
Well, exactly. They couldn't fall too far in this case. So then the final set of tests was what you can see on the slides here. So loading came now from a combination of a lot of individual paving slabs, effectively, loaded up, and roughly 2.5 tons per layer of these blocks, and 6 layers, and then water tanks on top of that. All of these blocks were placed manually by me and some friends, and took a while, and we didn't put them on randomly. We tried to put them on so that we achieved a uniform loading throughout the addition of these things. So the total load with all of the slabs plus the water tanks was about 20 tons. And that is beyond the total factored loading that would be applied to one of these bridges in practice, and quite a lot beyond what it would ever be expected to actually see in practice. And we had over here some local students who were also sort of walking up and down on the bridge for some vibration testing. This was the bridge testing team. So it's myself and some postdocs and one of the technicians from our lab. And when it passed the test and survived the load, there's our celebration. And of course, we've got a lot of data now from this bridge, which we've analyzed to try and understand how the bridge performs and ultimately make sure that we're confident that it was safe. And we were able to do that. We had a finite element model being developed in parallel with the bridge, with the construction of the bridge. It was, we validated it sort of on a continuous basis. We were learning more about the bridge and its material during the whole process, so we were constantly improving the model. We used measured material properties. We used a finite element software called Abacus. There's close to 1 million shell elements. That's quite a big finite element model, but still quite manageable to run. And we carried out what are called geometrically and materially non-linear analyses, which are the closest to replicating reality. And the model allowed us to look at more load cases than we could look at through the physical testing alone. So here you can see the components of the model. The basis of the model, or the basis of the geometry of the model, was the same digital model that was used to print the bridge. And we also did some laser scanning of the bridge to see how close its geometry was to what it should have been, and it was very close. Just some of the details of the elements of the model and the mesh. And then, of course, we wanted to validate the model to demonstrate that it could actually replicate the observed structural response. This is just one example where we've got one of the horizontal loading cases. So load on the vertical axis and deflection on the horizontal axis. The test and the FE curves are in pretty close agreement, showing that we're able to capture the behavior quite well. So that was under horizontal loading, and this is under vertical loading. And again, we're able to match the behavior quite well. And then, like I said, once we had validated the model, shown that it could replicate reality quite well, we could also look at different load combinations. And what we found is that the critical load combination was when we had the maximum vertical load mainly from pedestrian traffic, and also the maximum horizontal load simulating people pulling in on the handrails. That gave the lowest sort of resistance, but showed that we had a good margin of safety against failure. So the bridge was taken by barge from the factory and put into place, craned into place over a canal in Amsterdam. And that happened in July last year. And the bridge was opened by the Queen of the Netherlands, and there was a bit of a celebration. The bridge is still there, which is good to know. So it's been there for over a year now, and it's being continuously monitored during its life to see how it behaves. It's currently got a relatively short design life, only 3 years. And this 3 years was set because we don't know much about the behavior. So many structures have quite a short design life to start with, which later get extended, subject to, its behavior being shown to be okay. So we'll see how that develops. Just a word on some more sort of general aspects about this, challenges, and also thinking about what might be next. So a big challenge for construction is the cost. And 3D printing, often you think, right, cost is going to be a problem. But actually this particular technology is relatively low cost. The hardware is a robotic arm and a welding torch, and the input material is weld wire. So it's actually not particularly expensive. Product and process variability and defects and so on, I think are a challenge. Normally when you produce a steel section, it comes from a major supplier of steel, which they have quality control processes in place and certification and so on. With metal 3D printing, you can have a fairly small operation, and that's likely to mean that there's less scrutiny and quality control. So this is something we need to think about for the more widespread use of this. We've got well-established standards and statistics and so on for normal steel. This is needed for 3D printed steel. And one of the biggest advantages of 3D printing is you can really put the material where you want it and where you need it. But that means also you've got more complicated geometries, and that makes it more challenging from a design point of view. And ultimately, we need to make sure that structures or parts of structures that are built in this way are safe. And I suppose with all of our work on 3D printing, that's what it all boils down to. We are looking at the opportunities and so on, but we're thinking, how can this be safely implemented in a widespread manner, but in a safe manner in practice? Future opportunities. So I think, this method of construction is going to complement rather than replace conventional construction processes. So targeted use, hybrid construction. I think there's likely to be further landmark structures. This technology can produce fairly unique offerings, which will be attractive. I think there's potential for wide use in structural details. So things like connections and stiffeners. When you have buildings, you need to join beams and columns. There's thousands and thousands of these types of connections around. 3D printing can potentially offer a more automated method of construction here. And this is really quite manual at the moment. I think there's scope for a bit more innovation and imagination. There's a group in Germany that have developed what they call a beam hook. It's quite a simple idea. And I think it's one of the limitations is really our imagination now, rather than what the technology can do. We need to think about how we can use this geometric freedom to produce shapes that are sort of optimal, but also functional. There's potential for in situ fabrication. So rather than having your structure fabricated in a fabrication shop and then transported to site, potentially it could be printed directly on site with a team of robots. And this small bridge over a stream was produced on site in Darmstadt in Germany. Something else we've been looking at is strengthening and repair. So this is a normal steel I-section column. And what we've done is we've added material through 3D printing along the flange tips. And this is a good place to add material in terms of the strength. We've also looked at different profiles along the length. So more layers of material in the middle, fewer at the ends. And what we found is that you can add maybe a few % of volume relative to the volume of the existing column, 3 or 4%, and gain more like 20–25% increase in capacity. So this is, you know, quite an efficient way of adding strength without adding too much material. And this could be both for existing structures, but also new structures. You could have, you know, a few layers of weld added to all columns and get that 20–25% extra strength without much more material. There's certainly scope for more optimized structures. This kind of shape is completely impractical to produce using normal manufacturing techniques, but using, especially at a construction scale, but using 3D printing, it's as easy to produce this sort of shape as it is, you know, just a solid block. So there's huge scope for optimization, I think. And various groups have started looking at this. And here's an example of some optimized trusses that have been produced as well. Okay, a few conclusions. So this additive manufacturing process, WAAM, wire arc additive manufacturing, I think is the most suitable metal 3D printing method for construction. There are other different ones, but with a balance of sort of cost, speed, and scale, this one is good. We've got some promising results at the material and member level, showing that it performs reliably. The MX3D bridge is a great sort of visual example of what can be done, and it's now passed its safety verifications. It's open to the public. I think optimization and additive manufacturing go hand in hand, and this is a really important part of the viability of the technology. You shouldn't just be printing eye sections. We can already produce those very efficiently. We should be making use of the geometric freedom to print more optimized shapes. There's definitely still some challenges to overcome before this can be used very widespreadly, and lots of exciting opportunities requiring further research, which are going to keep me amused for some time to come, I'm sure. And with that, I'd like to finish and welcome any questions.
Thank you very much indeed. I'd like to begin. There's some questions coming up, but I'd just like to ask a little bit of history. What prompted the bridge? Who came up with the idea? Did they go to Arabs and Arabs said, "Oh, we want to print a bridge," or did the client say, "We want a printed bridge"? How did that take place?
Yeah, no, good question. It's the company MX3D, a relatively small operation, and that they started working on this technology, producing mainly sort of sculptural things and furniture, tables, this kind of thing, with unusual designs for people to buy. And they were very popular. And they then thought, well, wait a moment, what else can we do with this technology? And they printed small structural things and shown that they, you know, they behaved okay. And they approached the local authority and said, would we be able to print something for the city of Amsterdam?
Wow.
And they, you know, got lots of sort of help in place, and there's various partners that are involved. And it started to become a reality from that point. But, you know, what became apparent is that they didn't know too much about structures. They knew a lot about printing, and that's where Arup came in, and then we came in, and, you know, we learned a huge amount during the process.
Right. And in your testing, it seemed to me that you were testing cylinders and cross section, or circular cross section, and rectangular cross section, but the elements in the bridge looked as if they were rather different, in fact, from that oval or different shapes. You must have tested out the relationship between what was going into the design and what you were testing. Am I right?
Yeah, no, that's right. So we tested, I showed the sort of regular sections that we tested, and quite a few of the elements of the bridge are actually fairly regular. There were circular cross sections. And the other reason that we wanted to look at regular things is so that we could benchmark their performance against things that we know well, conventionally produced circles. But we did also produce and test elements that were oddly shaped. And
all right, so you did in fact subject them to the standard tests you were developing.
Exactly, yes, we did.
Bill, are we going to suggest that our guest, our members, ask their question? Alan Gilbertson has
if people want
one.
to, then I can allow people to unmute.
Yeah, I think that'd be sensible.
So
Alan, are you there?
Yep. I think, Alan, you should be off mute.
Is he on video? Well, perhaps I'll ask it for him if he's not.
It says his microphone isn't working. So, Rod, if you cover them.
He says, what was the butt joint between tubular elements, and how is the strength of the butt joint assessed?
So I think I guess this is referring to how the bridge parts were joined together.
Joined together, yes.
Yeah.
Different elements, I guess.
Yeah, so the bridge parts it was printed in 4 2.5 meter lengths, and those bits were then fabricated together by a professional fabricator. And the butt weld material was the same as the material used to print the bridge. And, in our testing and so on, that wasn't a weak point. And that's the idea of a butt weld, that it isn't a weak point. You've got, the same strength as the surrounding parts.
Thank you. And Bob has asked, has there been any similar work in aluminium structures?
Yeah, so I mean, with this method of printing, pretty much anything that you can weld, you can also print. And so there has been work on normal steel, aluminium, stainless steel, titanium, this kind of thing. And in fact, the aeronautical industry have started to use this quite a lot. And there are bits on aeroplanes that have been 3D printed that are flying around now. So the more sort of exotic materials, you can print them and they're in service.
And presumably that's because you have weight, reduced weight.
Exactly.
And additional strength.
Exactly. So typically we wouldn't use those grades for construction because their, weight is less of an issue for things that don't fly. And, it's a normal steel with the majority of structures.
Howard Bromley, are you around, Howard?
Yeah, I'm here.
We had a terrific echo there, Howard. Went on and on.
Spectacular. So it's much weaker along the line of the welds, and presumably has to be made thicker and heavier. What can be done to overcome this issue?
Yeah, so it's not actually much weaker. It's really the ductility that is the issue in that direction. So in terms of strength, it's not so much different. It is different, but it's not so different in the different directions. It's mainly this ductility that is damaged. That there's been, and this is very much an evolving field, but optimization of the printing strategy so that the sort of lines of the weld flow with the direction of stresses is an area that's being looked at to try and avoid this loading the material in its weaker direction. I think especially in the early days, we are also just going to have to use higher safety factors because of the greater uncertainty. And with time and with confidence, they can be reviewed and so on.
Yeah, Rod, can I just pop in a question on that?
Of course.
I'm interested because you're kind of hinting at it there around understanding of the fracture mechanics. I guess this is a bit of a novel area, hence the 3-year design life. How much of the fracture mechanics do you know at the moment?
Yeah, well, we've focused our attention mainly on sort of mechanical properties, buckling, stability, these kind of effects. But of course, there's lots of other things that are important: fracture, fatigue, and there has been work done on this. For the bridge itself, it's made out of austenitic stainless steel, and this is a material that has a very high fracture toughness. And the relatively few tests that were done demonstrate that it's not so different from normally produced material. With the fatigue issue, so a bridge is subjected to constant cycles of loading, and if you look at the machined material where the surface finish has been removed, again, fatigue performance not so different to normal material, but those surface undulations, they create stress concentration, stress hotspots, and that definitely has a negative effect. So the sort of thinking is, if you've got a fatigue critical structure, you're going to have to be quite careful with this. This is normal in normal construction. We still have welded joints, and we have to be careful with the welds, and sometimes they're treated to streamline the profile and that kind of thing. But the initial studies are showing that it's pretty good, but there's definitely a bit more work to be done on this area.
Okay, thank you.
You mentioned in your presentation about strengthening buckled beams, and I think Alan Gilbertson has picked up on that in his question. Does the weld process work for any steel material? And so is its future helping to restore damaged steel structures?
Yeah, so I think this is definitely something that we're thinking about. So more and more, we've got structures that are getting older. They need to be looked after. Loading demands on them is often getting higher, and they're deteriorating. Corrosion, fatigue, this kind of thing. So strengthening bridges and other structures is a big area. And there's different ways you can do it. And one way that is quite common is to take plates and bolt them or weld them onto existing structures. And that can be effective, and it is effective, but it's not always that easy to bolt plates onto surfaces which are not that smooth and flat and this kind of thing. And it's also not that easy to put the material exactly where you want it. So this offers another option. Pretty much you can print onto any existing material, though there's quite a lot of cast iron bridges around, and I think they'd need a little bit more care. A steel bridge should be perfectly okay to weld onto, but cast iron is something that we need to think about a bit more.
Thank you. And Azad Ayub, a practicing civil engineer, has said, could you give an idea of the cost per square meter of in this unit or any unit?
Yeah, it's quite difficult to give a cost, and this isn't an evasive answer. But if you simply look at the raw materials and the electricity needed to produce, 1 kilogram of 3D printed steel compared to 1 kilogram of normally produced steel, say, it's probably about double, somewhere around there. But I don't think that's a very good way of thinking about it, because, and in some cases more, it does depend on what you're printing and how much the more exotic the material, the fundamental cost is high, and the 3D printing bit of it is quite small. Whereas the more regular the material, the 3D printing bit of it becomes more expensive. But actually, I think what we need to really do to think about costs is to consider the whole operation, comparing what you would do to produce a normal bridge, manual welding, transportation, size of material, compared to 3D printing bits of it, more automation, less material should be used in total. and that kind of thing. And we're working with a local fabricator in London who thinks that, you know, labor costs are high and only going up. It's hard to get skilled people. This is, you know, possibly the future way of fabricating. And they think it will be commercially viable, you know, in the relatively short future.
Interesting. That's very interesting. Howard, are you online to ask your growing plants on the surface, because of the surface is so textured? Are you concerned about growing of vegetation?
Yeah, that's a good question. I mean, the surface finish is, some people sort of think, what's happened to your bridge? You know, there's something wrong with it. Some people think it looks, you know, unique and interesting. How it performs in the long term, both from a sort of, you know, stuff growing on it, but actually maybe more concerningly corrosion and, you know, material sort of getting locked into some of those grooves. There's been very few studies really. Preliminary studies suggest that things are okay, but these sort of effects need time really in order to tell.
Do you have a cleaning regime, or do they have a cleaning regime?
The bridge has no cleaning regime at the moment. You know, it is made of stainless steel. Stainless steel has naturally got good defense to corrosion, but it's not, as we know, it's not fully corrosion resistant. At the moment, it's being left, you know, with the weather washing it, but nothing else.
I'm not sure if we've lost Rod at that point. He's looking
Just lost
slightly.
Rod for a second, yeah.
Yeah, I think we have. Oh, so I think Alan, we have another question from Alan. A question about revisiting the low ductility across the print lines, avoiding need for plastic adaptation.
Yeah, the question's just disappeared there for me, but
Yeah.
we, you know, knowing different properties in different directions, we can certainly adapt our design to take that into account. And in fact, some 3D printed material can show quite significant strength and stiffness properties in different directions as well. So it can be quite anisotropic. And, you know, the initial reaction is, oh dear, that's bad news. We like material that is nice and regular and consistent in different directions. But actually, if you know the properties and they might be stronger and stiffer in one direction, you can potentially use that as part of the strategy for designing your structure. So I think, yeah, there's a lot of scope for that kind of thing.
I guess that's as you would for any composite material.
Yeah, no, exactly. And, you know, some of the material modeling that we've been doing is very much based on what composite people know a lot about.
Do we have you back, Rod?
You're on mute at the moment, Rod.
How about that? Sorry about that. I was saying, do we have any further questions? I think it's absolutely fascinating bridge. And it reminds me of Calatrava's work too, who worked particularly in concrete, but made bridges of great shape and subtlety. And seeing this bridge in Amsterdam is quite wonderful. If there are no more questions, perhaps David, are you online there?
Yes.
I would like to say a few words of thanks.
Thank you very much. Well, thank you, Rod, but thank you particularly, Leroy. It's a great story. I very much enjoyed it, and I imagine everybody who's tuned in. So thank you very much. I kind of hope we'll get you back sometime. And I would also like to thank everybody for the questions, because I think it was a very interesting open session. personally, I learned an enormous amount. So I trust that's shared by everybody else.
Well, of course, 3D printing is being used in space to make tools that they didn't carry with them.
That's right. Yes. In fact, 3D printing is certainly a space issue. But then, of course, there are all sorts of reasons why it's particularly useful in those circumstances. Okay, so I think I should close now with a vote of thanks for you, Leroy. So perhaps people can join me in clapping. Because that's what I'm muted.